Hello everyone, welcome to my channel. If you are new to my channel, please subscribe to my YouTube channel, so you can join our tech family. If it is informative to you, please like our video, share it with your friends so they can get help with these video, and don't forget to press all notification bell icon so you get regular update and don't miss any single video.
Welcome to the very last video in this series. It's taken a long time to get this far, so if you've been watching since video 1, I'd like to thank you for sticking with me all this way. We're going to finish up by looking at the spanning tree protocol in more detail, to see how it finds loops and how it selects which links to block. So we saw that spanning tree prevents layer 2 loops in our network. It does this by finding potential loops and then blocking one of the links to stop the loop from forming. Let's see how it does this. To start with, spanning tree running on one switch needs to discover other connected switches and share information with them. It will send out a special frame called a Bridge Protocol Data Unit, or BPDU. There are two types of BPDUs. This one is called a Configuration BPDU. Initially, these messages enable switches to learn if there are any other spanning tree enabled switches nearby. Did you notice that we started with a single switch and worked our way out from there? In a spanning tree topology, one switch is nominated to be the root bridge. Spanning tree is better thought of, as the name suggests, a tree shape, or maybe an inverted tree shape. At the very top of this tree is the root bridge. Let's focus our attention on the root bridge for now. The root bridge will send configuration BPDUs outward to other switches. These are sent out on all ports by default. Other switches may send BPDUs to the root bridge too. This depends on the version, which we'll discuss briefly later. The root bridge assigns roles to its ports that connect to other switches. Ports that face away from the root bridge are called designated ports. Other switches have some ports facing toward the root bridge and some ports facing away. One port on each switch, the one closest to the root bridge, is called the root port. The root bridge can't have ports facing itself, so it never has any root ports. Ports facing away from the root bridge are the designated ports. But wait, a loop is formed in the network. Spanning tree needs to do something about this. First, it needs to detect this loop. But how? Let's take a step back. When a switch sends a BPDU, it will put a bridge ID in there. This ID is unique to each switch. So imagine now that the root bridge is sending configuration BPDUs to its connected switches. In our example so far, there's 2 of them. They receive these BPDUs and know they're connected to the root bridge. As part of the spanning tree process, they also forward these BPDUs onto other switches. So in our example, these 2 switches will forward these BPDUs to each other. Now they will independently be able to see that they have 2 paths to the root bridge. There should only be one, so this is how they know that there's a loop. It is at this point that each switch needs to decide which ports are root ports. Remember that each switch makes its own independent decisions based on what it has learned. As we have said a few times, the root bridge doesn't have any root ports, so that part's easy. It makes all of its ports designated ports. It's a little bit more complicated for the other switches. Each port has a cost, which is based on the speed of the link. The higher the link speed, the lower the cost. So for now, let's say that the cost of each of these ports is 4. That's not very helpful yet, as they're all the same. The useful part is that the switch measures the total cost to reach the root bridge. Think about the root bridge sending BPDUs again. The 2 switches receive the BPDU and decide that the cost to get to the root bridge over these links is 4. These switches update the BPDU with the cost of 4 and send them out the other interfaces. So when these BPDUs are received, the switch adds the cost written in the BPDU message to the cost of the interface it was received on. In this example, the cost to get to the root bridge, using these paths, is 8. The best path to the root bridge is now clear. These ports become the root ports. It's also clear which link should be disabled to prevent this loop. But how is it done? Do both these switches disable their ports, or does just one of them do it? The short answer is, only one end of the link will be disabled, and the end that's selected comes down to the bridge ID once again. The one with the lowest bridge ID will set its port to designated. The other will set its port in a blocking state. These three switches have now fully converged and can forward traffic without the risk of looping and broadcast storms. Of course, this process needs to happen throughout the entire network, which can get more complicated as we move through. Does it end here? No, the root bridge will continue to send BPDUs out regularly. The other switches will continue to update the cost and forward them out. This mechanism is like a heartbeat. It tells the switches that they have a valid path through to the root bridge. If the BPDUs suddenly go missing, then there is probably a dead switch or link somewhere. Okay, it's quiz time. Have a look at these simple topologies and see if you can figure out the answers to these two questions. Under normal operation, this topology is quite stable. But what happens if a switch dies? Firstly, it won't be forwarding BPDUs anymore. Nearby switches will notice the loss of BPDUs and know that the switch is gone. The spanning tree topology then goes through a reconvergence process. Switches may need to update their port types. But there are other changes that can happen in a network. We might add a new switch or link. This would also cause reconvergence, and the port types could change again. Basically, anything that causes a spanning tree port to go up or down, or change the flow of BPDUs, will cause reconvergence. The next step is to think about how the rest of the network learns about these changes. This does not just rely on the configuration BPDUs that the root bridge sends. There is a second type of BPDU called a topology change notification, or TCN. These are sent by regular switches, not the root bridge. TCNs are sent only when there's a change in the topology. If a switch receives a TCN, it will generate its own TCN and forward it on. Eventually this filters through to the root bridge. At this point, the root bridge will update its configuration BPDUs if necessary. These continue to be sent out regularly as normal. The process of flooding BPDUs, finding loops, and selecting ports is not instant. You might be wondering then, how does spanning tree prevent loops before this process has completed? Well, by default, every port on a switch goes through a particular process before it fully comes up. This lets the switch decide if any given port is connected to an end device, like a printer or workstation, or if it's connected to another switch. A loop can't form on a port connected to an end device, but it can on a switch-to-switch link. So when the port first comes up, probably because we've enabled it or plugged something in, it will start in the blocking state. This stops the loops from forming right away as no data can pass. The only exception to this is BPDUs, which are allowed to flow. By default, the port will remain in this state for 20 seconds. Next, the port moves into the listening state. A port in the listening state can be a root or designated port. While in this state, the switch will process any BPDUs it receives in order to learn about the network. This may cause the port to transition back to blocking if needed. Regular data still does not pass through this port yet. The listening state lasts for 15 seconds. Keep in mind that this is happening for all ports, not just ports connected to other switches. After the listening state, the port moves to the learning state. During this state, the switch does what all switches do all the time. It learns MAC addresses and builds the MAC address table. This state lasts for 15 seconds, and still regular data cannot pass through this port. Finally, the port transitions to the forwarding state, and regular data can now flow. The port will remain in this state until some topology change requires it to go through the process again. As I said in the last video, spanning tree has been around for a long time, at least in IT years. Everything we've been discussing so far is the original spanning tree standard, also called 802.1d or classic spanning tree. But there's a few downsides to classic spanning tree. We saw one just a moment ago when we realized that it took 50 seconds for the port to come up. So to address this and a few other issues, some newer versions of spanning tree were developed. We're going to take a brief look at these improvements. First up, Cisco released per VLAN spanning tree as a proprietary solution. Classic spanning tree will block links for all VLANs at once, but PVST treats VLANs individually. This means that, for example, one link may be blocked for VLAN 1, but a different link will be blocked for VLAN 2. This means that the network can be used a bit more efficiently, as you don't have entire links sitting around idle. Later, they updated this to PVST+, so it could be compatible with Classic Spanning Tree and therefore with other vendors. They also added some enhancements that would treat end device ports differently to ports that connect to other switches, so you wouldn't have to wait 50 seconds for your workstation or printer to come online. The next standard to come along was Rapid Spanning Tree, or 802.1w. This was standards-based, so all vendors could use it. This standard still treats all VLANs the same, like Classic Spanning Tree does, but it changes the way the port states work as well as their timers. It no longer takes 50 seconds to bring switch-to-switch links up. Cisco liked these changes, but they also liked the idea of treating VLANs individually, so they created another of their own standard. If you hadn't noticed, Cisco are kinda known for doing that. So they released Rapid Per VLAN Spanning Tree, all the advantages of RSTP and PVST in one protocol. Once again though, this is Cisco only, so other vendors can't use it. And finally, the rest of the industry caught up and created Multiple Spanning Tree, or 802.1s. MST is quick, like RSTP, but it handles VLANs better. In fact, it handles VLANs a little better than PVST and RPVST, as it considers groups of VLANs when creating spanning tree topologies, rather than considering each VLAN individually. This approach puts less strain on the switch and its resources. And now the final quiz of the series. I hope you've been finding these quizzes useful.
We hope you enjoyed the video and found value in the content. We value your feedback. If you have any questions or suggestions, feel free to post them in the comments section or contact us directly via our social platforms. Thanks for watching.